I'm Reverend Greg, and I welcome you to this video in the tutorial series Shaders for Hobby Programmers. In this video, we'll create this side-scroller water surface shader. I will explain each step, but I won't explain every detail since everything we need to know to create the shader was covered in another video tutorial already. In the last few videos, we learned a lot about fragment distortion and distorting with maps, and in earlier videos we covered color effects like Photoshop blend modes. Despite not covering all the basics, this is going to be a rather long video. I just hope it won't be too boring or too fast, so just leave a comment if you think the pacing of this video is off. I'm curious about it. But as always, a short disclaimer first.
This tutorial series is mainly for hobby programmers who struggle with understanding shaders. I'm not a professional programmer and I'm not very good at maths, so if you see any mistake in my video or see a better way to solve a problem, please add a comment so everyone can learn from you.
Before starting, I'd like to talk about two important limitations of this method. First being, this is not a water simulation, so we can't just place a rock in the water and expect the water to flow around it. It's just a distortion effect trying to look like a water surface. And second, the reflection completely ignores distance of the reflected objects. Let's say we got this background, sky and water surface. We got some rocks in the background at different depths, and a bridge in front of these rocks. Then this is what the reflection should look like. Each item is reflected at the line where it touches the water surface. For the sky, that's the horizon. If we draw the reflections that way, we'll have to draw each object twice, the original to the application surface and the reflection to the reflection surface. And this can get complicated and will definitely cost power. So instead, we're going to ignore depth and simplify by a lot. We won't be able to draw a bridge, but a dam instead. And now everything is connected to the horizon like this. Then we just copy the application surface and draw it mirrored along the horizon. So instead of drawing everything twice, we just use a copy. It's still wrong. We still ignore distance and angles, but it will be fast and still look good enough for this use case. That said, at the end of this video tutorial, I'm showing a method to respect depth and position if you want to. The ducks in the preview are an example of how it could be done. So we're going to build this effect step by step. We need to get the reflection of the game onto the surface and then distort the reflection. To make it look like water, we'll blend the reflection with a solid color using Photoshop blend modes. And we'll add some basic color adjustments like brightness, saturation and contrast. Then to improve the look further, we'll mix that colored reflection with another solid color. The darker the reflection is, the more of that other color it will receive. After that, we'll add a waterline to make it look more like a body of water. And in the end, we'll add some rubber ducks to show how you could add flotsam or boats or other stuff that need to respect depth. Let's have a look at the project first though. There are a few sprites here. From the base project, I'm using the Sunnyland sprites created by Zuno. Links to his Patreon and open game art sites are in the description beneath this video. We're going to use the tile set and the two background sprites. Then I also added some sprites specific to this tutorial. A water object sprite so we can see the water object in the room editor, a distortion sprite with 3 different leopard patterns on each color channel. The patterns all need to tile seamlessly. And the sprite needs to be on a separate texture page, needs to be square, and its dimensions need to be any 2 to the power of n. And then the waterline sprite, it's just 1 pixel, its color is white, and its alpha is a bit less than 0.5. And finally the duck sprite. Its origin should be rather low, since we're going to flip it for the reflection. We're going to look at the shader and the main object later, so let's have a look at the other objects next. I've used the base project's wall object to add solid collisions to the mockup game. It's not really important for the shader effect to work. The object waterside background is just a very simple parallax background object drawing the 2 forest background images from the base project. Again, not important for the shader and just part of the mockup. The play object is just a very simple object to move around the demo. Again, not important for the shader to work. And finally the duck object. And this is part of the tutorial, but the code in it is simple. We're going to look at it when we add the ducks to the game. And this is the room. It's a bit more complicated than usual in my tutorials. One reason is I've created a small mockup game with different layers, and the second reason is I wanted to have lots of shader variables be dynamic for the tutorial, and thus I needed lots of sliders and buttons on the GUI. And this instance layer is the parallax background object, On the next 3 layers is the mockup game's tile set. Then there's the wall layer for collisions, the main layer with the player instance and the water effect instance, and the duck layer with all the duck instances. Now on the GUI layers I added lots of GUI elements. We got 20 sliders in this creation order and 4 toggle groups with 1 or 4 toggle buttons in each. Now this is the main object water side distortion. So let's have a look at its events. In create event, inside the title region, as always, is just some description and stuff needed for the demo project, but not for the shader effect to work. The same goes for the GUI region. I'm just setting up the captions of all sliders and toggle buttons and their initial values. The important stuff is in the sprite and shader region. Here I'm setting up the distortion sprite, that's the one with the 3 leopard patterns, then the shader and all its uniforms. Mind that most of those uniforms are only needed to find interesting settings. Once you got what you want, you could and should turn as many of those uniforms into constants or macros. UDistortText will send the texture ID of the distortion sprite. UWaterShiftRGB will be used to move the 3 leopard patterns along the X or Y axis to create a flow. UDistortStrength sets the distortion's strength. UPatternSize will send a scale factor for the distortion maps and thus changes the size of the distortion. UWaterCol is the second solid color we'll mix the reflection with. The first color we'll use to apply the Photoshop blend modes will not be sent as a uniform, but as a vertex color instead. Then UColMix will determine how the reflection color is mixed with the watercolor. UBirdSatCon will be used to change brightness, saturation and contrast. UBlendMode is for testing only. With it, we'll be able to dynamically change the blend mode from overlay to soft light, hard light and vivid light. And finally, UShowResult is for debugging only. With this, we'll be able to show the distortion maps instead of the water reflection. Then after setting up the shader stuff, we'll also need some other variables. DistortText is the ID of the distortion texture. WaterShift R, G and B are going to change each step to make the water move. And SurfWater will be the surface ID we draw the reflection on. So the create event looks like it's a lot, but that's mainly due to this demo setup. In a real game you'd only need the shader, the distort sprite and only some of those uniforms. Now in cleanup event I need to reset the demo project's camera because the mockup is scaled by factor 3 and I just need to reset that factor to 1. But for the shade effect only the second line is important, freeing the water surface to prevent memory leaks. The step event is as simple as optional. I'm just moving the water object up and down in a sine wave behavior. It's absolutely unnatural, but for some reason I like the effect anyways. Draw event is empty and just here so the water dummy sprite won't be drawn. And all the important drawing stuff is in the draw end event. So after everything in the game has been drawn to the application surface. Again, due to the demo nature, this event looks like there's a lot, but most of it is just to keep the effect as dynamic as possible. In a real game, you wouldn't need half of the code here. Step 1 is creating the water surface with the reflection of the application surface on it. Before looking at this code, let me explain how we're going to do this. This is the game without the water effect. And the red line is showing the Y position of the water instance. This is going to be the water level. To get a reflection, we need to create a surface for the water. It's as wide as the application surface and its height will be the distance from the waterline down to the bottom of the view. Then we can draw the upper part of the application surface to the water surface with a negative Y scale. Then to make this look more natural, we squash the water surface. This will create a black bar at the bottom for now, but later we'll fill that with a watercolor and the distortion will make it look really good. After that, we'll add some optional stuff. First we can create a smaller surface, draw the application surface's upper part scaled down to the water surface, and then draw the water surface scaled up back to the application surface. Like this we can work with smaller surfaces, but depending on art style or game resolution, it might look good or horrible. Especially in pixel art without subpixels, as this demo project is, it looks just awful if we downscale by a factors less than 0.66. This reflection in example is scaled by 0.5, and this by 0.25. And finally we'll add a toggle to either set the linear interpolation filter on or off. However, as you will see, this won't fix the scaling issue. Now the code. For now, I commented out everything we won't need for this step. The first thing we need to know is if the water surface with the reflection on it would be in the view, because if not, we won't need to create a reflection at all. So we need to know where the view currently is, and we need to know the height of the application surface. We're inside the water object's draw end event, so we can compare its y position with the view's y position plus the height of the application surface. If the water instance's y is smaller, then we're drawing the reflection. And all the way down, if the water is not in view, we'll just draw circles as debug information. We'll use those circles for more debug information later. Now, if we draw the water surface, then we need some more information. Water y scale is the squashing factor I just described. The value is taken from slider 0, and the lower the slider is, the more of the reflection will be squashed vertically. It must never be 0 though, because later we're going to use it as a divisor. Water level is the waterline's y position on the view, so we can subtract view y from the water instance's y. The water surface's width is the same as the application surface width, and the water surface's height is just the difference of the application surface's height and the water level. But it needs to be at least 1, since the surface height of 0 is not allowed and would throw an error later. The reflection height is the height above the waterline that fits onto the water surface after squashing it. But let me explain this with an illustration. We're going to draw two scenes at different positions in a split screen. In the first scene, the player character is very close to the water surface, which means the surface is quite tall. The water y scale factor is 0.5, so the reflection isn't filling the entire water surface. That's why we got a black bar on it. Now the application height is of course the height from top to bottom. Water level is a part of the application surface above the waterline, and the water surface's height is the remainder. Now the reflection height is the part of the application surface above the waterline that would fit onto the water surface. If you look at the code, you see we're using a min function. If we take the first attribute, surf water height divided by water y scale, which in this case would be surf water height times 2, would get a reflection height that is much larger than the water level. Means we would try to reflect things that are not on the application surface anymore. The second attribute in the min function is smaller though, it's just water level. So we're using everything above the waterline to reflect onto the water surface. Now in the second scene, the player character is farther away from the water surface. Of course the application surface's height stays the same, but the relation of water level and surf water height was changed. The waterline is much lower on the screen, and thus the water surface's height is a lot less now. The reflection height again is the part of the application surface above the waterline that would fit onto the water surface. If we'd take the second attribute in the min function, like we did in the other scene, this would be reflection height, the same as water level. But you can easily see we draw more than fits onto the water surface, so the reflection height is too tall now. So in this scene, the first attribute of the min function is smaller. This time we set reflection height to the water surface's height divided by the water y scale factor. You might have noticed I'm also subtracting 2 from the reflection height. That's for a later step really. But back to the code. The last information we need is the surface scale factor. This will be determined by how much the water surface is scaled down to draw upon and scaled up to draw back onto the application surface. I'm grabbing that factor from a toggle button group. It's either going to be 1, 0.75, 0.66, 0.5 or 0.33. With all that information we can now draw the reflection onto the water surface. First we'll set the linear texture filter on or off depending on yet another toggle button. Then we check if the water surface exists, if not we'll create one, and if it does we'll resize it. Its dimensions are surf water width or surf water height times surface scale. After that we can set the render target to the water surface, clear it to black for now, and then draw the application surface onto the water surface. We'll need the function drawSurfacePartX for this. We're drawing the application surface, the left attribute is 0 and the top attribute is water level. The width attribute is surf water width and the height attribute is negative reflection height. Doesn't really matter that we flip the top and bottom like this. The X scale is just the surface scale factor and the Y scale is negative water Y scale times the surface scale factor. So we flip the image horizontally. And the vertex color is just white with alpha 1. With this, the reflection is on the water surface and we can reset the render target. Now all we need to do is draw that surface at view X, instance Y scaled up by the surface scale factor, without rotation, and white 1 again. And then we can set the texture filter to false again because we're drawing a pixel art game. So this works. Reflections are in. And the squashing slider works as well. So does the surface scale factor. And the linear texture interpolation toggle. But as soon as we walk around, the reflection starts to flicker a lot. It's the same problem as in the scale blurring video. When scaling down, we lose pixel information and pixels just pop in and out depending on the camera's position. Now this is a pixel art mockup without subpixels. I'm guessing with subpixels this wouldn't flicker as much, or at all though. Up here we can see the 2 white circles in the top left corner of the view, so we know at the moment the drawing code is completely skipping the water surface stuff because it's not in view anyways. With a scale factor 0.75 it looks acceptable. Especially once we distort the surface, the flickering would be nearly gone. And of course, with the linear texture interpolation on, the flickering is less noticeable as well. Now let's distort the reflection. This part is pretty much what we did in the previous videos. In the tunnel distortion video, I explained fragment distortion in general, and in the heat haze, flag and flame distortion videos, we were already using distortion maps. We're back in the draw end event of the water object and we'll need to add a few more lines of code now. The first 3 new variables are water shift R, G and B. Those will be used to move the distortion patcher along the X or Y axis. In create event those 3 were set to 0 and here we're constantly adding or subtracting to them. In example, water shift R is constantly adding slider 1 times 2 minus 1. So if slider 1 is 0, water shift R will be decreased by 1 each frame, which means the distortion pattern's red channel will shift 1 room pixel per frame. If slider 1 is 0.5, water shift R will not change, and if slider 1 is 1, then water shift R will be increased by 1 each frame. The same goes for water shift G and for water shift B. Strength X and strength Y will be used as distortion factor, but that's nothing new in this tutorial series. And finally, pattern width and height are the distortion pattern sprite width and height multiplied by a factor. With this we can determine the scale of the distortion pattern more easily. I've already set the factors to slider 6 times 2 and slider 7 times 0.25, and it's less for the height because I want the distortion pattern to look stretched in the x-axis. I've used the max function to keep the variables above 0 because inside the water shader will divide by this. But actually it wouldn't be that important. A shader just returns 0 when dividing by 0, and frankly if pattern size is 0, there's something awfully wrong with your code anyways. But we'll see how these factors work when we run the demo later. Show result will be used to tell the shader to draw the pattern instead of the distorted water reflection. So this will help us understand the scale factors, the water shift RGB movement and so on. Now the creation of the water surface is unchanged in this step. Now we got everything we need for the shader. So instead of just drawing the water surface back to the application surface, we need to set up the shader first and reset it afterwards. The uniforms we need for now are the Vec3 water shift RG and B, the Vec2 distortion strength, the Vec2 pattern size, and the float show result. And of course we also need to pass in the distortion texture. Then we can draw the water surface to the application surface and reset the shader. The rest stays the same, so let's move to the vertex shader. Very early on in this tutorial series we learned about different coordinate systems inside the shader. In example, VV text code is a coordinate system based on the texture coordinates of the base texture. And in position is a coordinate system based on the room's x and y coordinates. Now here we'll create our own coordinate system. It's in texture coordinates for the distortion maps, but it's based on the room coordinates as well. Like this we can control the movements of the distortion maps, but at the same time tie the coordinates to the room. So when the camera moves through the room, the pattern won't. Let me once more try to explain this with an illustration. This is the image already distorted, and above that is the code in the object and the vertex shader. The distortion will happen in the fragment shader though. In the vertex shader we just built a coordinate system for that. Let's have a look at water shift R, G and B first. In create event we've set those to 0. In draw end event we in or decrease them by something from -1 to +1 each frame. Then we send those 3 variables to the vertex shader as a Vec3 uniform. Now in the vertex shader we create 3 new varying Vec2s, I called them VV position R, G, and B, and those will be a coordinate system for the red, green, and blue color channels of the distortion map. And in the main function of this vertex shader, we create those three coordinate systems. We start with inPosition.xy. Those are the room coordinates of each vertex. So if the top left vertex of the water surface is x100, y200, then inPosition of that vertex is the same, x100, y200. Then we subtract a vec2 built from water shift RG or B and 0. In the coordinate system for the red and green channels, we subtract water shift R or G from the x room coordinate, so we're shifting the coordinate system along the x-axis. And in the coordinate system for the blue channel, we subtract water shift B from the y room coordinates and thus shift the coordinate system along the y-axis. Then we divide that by pattern size. So let's have a look at the pattern next. This is the pattern sprite with its three maps on the red, green, and blue channel. And this is the pattern if we would pick samples at VV text code, since pattern is on a separate texture page and the base texture is the surface. So both images UVs range from 00 to 11. The result would be a stretched pattern. Now in draw end event, we stretch the pattern's width by factor 2 and its height by factor 0.25. The result would look something like this. Or like this if we reduce brightness a bit. Now let's go back to the uniform vec2 pattern size. Pattern size is built in the draw end event. It's the pattern sprite's width and height in pixels multiplied by a scale factor. So it's still based on pixels. In the vertex shader inside the main function, we calculated a constantly shifting coordinate system based on room coordinates, so kind of pixels as well. Now dividing the shifted position in pixels by pattern size in pixels, we'll get the coordinate system in texture coordinates. Those coordinates can of course be below 0 or above 1, but we'll have to fix that in the fragment shader with the fract function later. Now if water shift R is positive 1, water shift G is negative 0.5, and water shift B is positive 0.2, this means the red pattern will move to the right by 1 pixel per frame, the green pattern will move to the left by half a pixel per frame, and the blue pattern will move down by 0.2 pixels per frame. The ability to move all three patterns at different speeds and in different directions is what gives the water surface a seemingly random distortion and which allows us to make the surface look like still water or flowing water. And since we tied the coordinates to the room coordinates, the pattern will stick to the room coordinates as well. So if we run around in our mockup game, the water distortion will not move with the player or camera. It will stick to the water surface. And that's it for the vertex shader. There's nothing else important here. We still need other vertex attributes and bearings, including the vertex color for this shader, and the vertex shader won't change for the rest of the tutorial anymore. The fragment shader, like the draw end event, has still several sections commented out. Here as well, we'll add them step by step. But let's have a look at what's in here for now though. In the header you can see the three new varying vec2 VV position R, G, and B, and the remaining uniforms. Vec2 distort strength for the effect strength, sample 2D distort text for the distortion pattern texture, and float show result so we can show either the distortion pattern or the distorted surface to debug. Inside the main function we first need to take samples from the distortion texture. So we grab a sample from the red, green and blue channel at VV position R, G or B and store the sample in a vec3 called distort sample. As mentioned, VV position now is in texture coordinates but could be negative or more than 1. To fix that, we'll just get the fractional part of VV position. Now all components of distort sample range from 0 to 1. If we'd use that, the distort direction would always be to the right or down, and I actually want them to go left and up as well. That's why I decreased distort sample by 0.5 before moving on. Now that we got the distort sample, we can create a distortion vector from that. This is a bit of a complicated line. We create a vec2 distort from vec2 distort sample.rg and multiply it by the float distort sample.b. So distort x is made of distort sample.r times distort sample.b, and distort y is made of distort sample.g times distort sample.b. Like this, we get control over the water's movement. Then we multiply both distort components by the vec2 distort strength, so we can determine how much the x and the y axis get distorted. And finally, we're multiplying both distort x and y by the float 0.2 plus 0.8 times vv textchord.y. This means the distort strength is again multiplied by factor 0.2 if vv textchord.y is 0, and by factor 1 if vv textchord.y is 1. Or in other words, the distort strength is reduced at the top of the water surface and increased to full strength at the bottom of the water surface. This will add some depth to the effect. Now with the distort vector we can finally get a sample from base texture. Vec3 base call is the sample call as RGB at VV text chord plus the distort vector clamped to 0 and 1, so the sample coordinates won't leave the surface texture. And that's it for the distortion. Now we just need to add the debug function to show the distort sample instead of the distorted water surface. So all the way down we got a new vec3 out call and mix base call and distort sample by the mix amount of show result. So if show result is 0, we'll see the distorted base texture, and if show result is 1, we'll see the distort sample's components. The last line of course is setting the output color, which is just a vec4 created from out colon 1. The distortion works now. With the strength X and Y uniforms we can set the effect strength. The X distortion should be kept rather low, but the Y distortion looks good on nearly any setting from 0 to 1. And with scale X and Y we can set the scale of the pattern. With speed R, G and B we can set or stop the movement. That's the uniform vec3 water shift RGB in the vertex shader. And with show result on the debug slider we can show the vec3 distort sample. To better see what the water shift RGB uniform does, I'll change the scale a bit. Now we can see the 3 leopard maps quite clearly. Water shift B will move the blue pattern up or down and thus gives the feeling of water moving towards the shore or away from the shore. Water shift R will just add some irregularities but will not change the flow of the water. And water shift G will move the green pattern left or right and will give the feeling of water flowing in that direction. Now I'd like to show and fix a small issue. I'm setting the squashing factor so that the black parts at the bottom of the water surface are just so visible. Now if I jump up and land again, you'll see that the black parts appear quite suddenly, and depending on the water level this can look glitchy even. The black areas are created when we cleared the water surface with black alpha 1, and the reason this only happens sometimes is that the black part only shows when the reflection is smaller than the water surface. Fortunately there's an easy fix. We just need to make sure there's at least a couple of pixels of blackness on the bottom of the water surface, which means we just need to reduce the reflection height by a bit. So back in the water object's draw end event we can just subtract 2 from reflection height and this will fix the issue. So if we run this again and set the same squashing level as before, we can see the issue is fixed. Actually, no matter where we are now and no matter by how much we squash, there will always be some blackness at the bottom of the water surface. Now all the complicated stuff is done. We just need to tweak the colors and make this look prettier. So the next step is adding a vertex color and blend that with the distorted water surface. We're going to simulate some Photoshop blend modes that work quite nicely with this shader. So now we need a blending color. I've set up 3 sliders for that so we can create an HSV color dynamically. Then for this demo project I also want to change the blend mode type dynamically, so I've set up a toggle button group for that. To tell the shader what blend mode to use we need to add the uniform blend mode. And here we also need to change how the water surface is drawn. Instead of setting a white vertex color, we'll set the vertex color to blend color. And now I'm adding one of the debug circles. This will draw a circle in blend call to the upper left corner of the view so we can see the blend color visualized. Inside the fragment shader we first need to add the blend mode uniform. And then the blending code. We talked about simulating Photoshop blend modes before in video 8b day and night cycle version 1.1, so I won't explain it here, but like then I've just used the formulas by Rogelio Bernal. A link to his site is in the description beneath this video. I've added the blend modes overlay, soft light, hard light and vivid light and used if statements to determine which blend mode to use. Once you decide which blend mode you want in your game, you really should remove the other 3 modes and the if statements. Branched code in fragment shaders tend to cost quite some performance, and the only reason I did it this way is for demo reasons. And now the debug line needs to be changed a bit. We're mixing out call now instead of base call. And then we can run this code again. And you can immediately see that the water is now colored. The blending color is shown in the debug circle in the upper left corner, and with the blend HSV sliders we can change that color. And with the blend mode toggles we can change the way this color is mixed with the reflection. We got the overlay, which just pushes the colors to its blue. The soft light, which does something similar but less saturated. The hard light, which looks more like tinting blue. And vivid light, which again pushes in a very saturated and vivid way. Now the next step, adjusting the colors in general. For some reason I wanted to add brightness, saturation and contrast. Depending on what you want to achieve, this might help or not at all. This is something we did many times already in this tutorial series, so there's nothing new to explain. We'll just need a brightness, saturation and contrast value from 3 more sliders. And we need to pass those values to the shader as a vec3. In the fragment shaders header, we now need to add that uniform vec3. And in the main function right after the blend mode section, we can add in the color adjustments. Brightness, saturation and contrast. Now let's try to get some filthy, dirty water with those adjustment options. And with these settings the water really looks uninviting, so I guess the color adjustments do help finding nice settings quickly. Next I'd like to replace those black areas at the bottom of the water surface with another color, and I want to tint the darker areas of the reflection with that color as well. We'll need 3 new variables. The first is the new color. Again, I've set up 3 sliders to create an HSV color dynamically. The other 2 variables are mixing thresholds. We'll see how those work when we look at the fragment shader. Mind that the first call mix ranges from negative 0.5 to positive 0.5 and the second call mix from 0.5 to 1.5. It's important that those ranges don't overlap and that the first range is lower than the second. Also, the upper end of the first value and the lower end of the second value should both be somewhere between 0.2 and 0.8. And now instead of clearing the water surface to black, we can clear it to the new watercolor. In the shader section we can now pass in the watercolor as vec3 and the mixing thresholds as vec2. And in the debug section I'm just adding in the second circle, which will be filled with the watercolor. In the fragment shaders header we need to add the new uniforms, vec3 watercolor and vec2 call mix. And in the main function after the color adjustments we can now mix the 2 colors. Again, this is nothing new in the series. We did that the first time I think in the video on duotoning. We're mixing watercolor and outcolor. The mix amount is a smooth stepped value. The value is the brightness of the base color, not the outcolor. The lower threshold is first call mix value and the upper threshold is the second call mix value. So if the value of base call is lower than the lower threshold, we'll get the watercolor. If the value of base call is larger than the upper threshold, we'll get outcall. And for any value in between, we'll get a smooth stepped mix of those 2 colors. Now with this, our fragment shader is finished. The remaining 2 tweaks are done in the draw end event only. So we can close the fragment shader here as well, but once you've found nice settings for the shader, you should definitely turn as many uniforms into constants as possible. So let's see how this affects the overall look or mood. First I'm picking a yellowish saturated orange as blend color. Now if I move the watercolor hue, you can see how it mainly affects the darker areas on the water surface. Setting the watercolor to a dark saturated blue adds a nice contrast between dark and light already. Now the lower mixing threshold mainly affects the darker values. And the higher that threshold is, the more it is considered to be dark. And the upper threshold determines how much the watercolor influences the lighter colors. With both at 0.3, we can improve that already nice contrast even more. And clicking through the blend modes again shows how they influence the mood as well. Here I really like the vivid light, although it doesn't really match the mockup level. What I still don't like, however, is the waterline. It feels like there should be a nicer border between water and shore, so we're going to add a line there. And this is going to be extremely simple. In the beginning I already showed you the sprite we're going to use. It's just this 1 pixel small sprite, its color is white and its alpha is just below 0.5. So all we need to do is draw this sprite stretched across the top of the water surface after drawing the reflection onto the surface. Technically, this would reduce the alpha of the water surface. In my tests, that was not an issue, but if it is in your project, then just add the 2 lines I commented out. The first locks the alpha channel and the second opens it. Now, this doesn't look perfect by any means, but it looks so much better than before, and this effect costs hardly any additional performance. And now the last step, how to draw things onto the water and get a reflection anyways. We're going to draw rubber duckies floating on the water, but since for some reason I wanted that effect to be toggleable, I'll just add this line of code here. Then, while drawing to the water surface, but after drawing the reflection and the waterline, I'm going to draw the ducks flipped upside down to the water surface. So I'm just referring to all duck objects and tell them to draw their sprites at their position in view, changed by the surface scale and flipped upside down. This will create the reflection. Of course, if you'd have different floating objects, you'd call a parent object here. And if you have lots of floating instances, you'd probably want to check if they're in view before drawing. Then, after the water surface has been drawn back to the application surface, I'm just calling draw self on all duck objects. Here again, if you've got different floating objects, you call the parent, and if you've got lots of instances, you'd want to check if they're in view first. Now the duck object I kept ultra simple. It just has a step event. If there's no water object, do nothing. The local var hspeed is just grabbing the movement of the green distortion map, since that's the one giving the illusion of moving water. X is in or decreased by hspeed, Y just sticks to the water instances Y in case that changes, flip the sprite according to the hspeed sign, and I just wrap the X position around the room sides. Now we got our ducks floating along the river, and they even have a reflection. However, the reflection is a bit off because there shouldn't be any above the ducks. Now 2 thoughts about what you can do or should think of when adding objects on top like the duckies. The first is, if you add more complex things, you can't just flip the sprite to draw the reflection. Let's take this boat as an example. If we'd just flip the image, this would be awfully wrong. The shape is wrong, the angles are wrong, and while we can look into the boat from above, we shouldn't be able to see the inside of the boat in the reflection. So we'd actually have to draw a separate reflection image to fix all that. And if you want to add a waterline, just draw a white line onto the reflection image like this, and it will be distorted automatically. The other thing is this. In the beginning of this video, I said we can only mirror along one single horizon line, like in this image. I claimed we can't do this where each object has its own depth, but actually that's what we did with the ducks. So yes, you can do this, but you have to find a performant way to do it, and reflecting tiles like that might be quite challenging. Anyways, I think this shader is really nice, although not being a fluid simulation, and I hope you like it too. I hope I found a pace for this video that suits most viewers. Next time I plan to finally add a shockwave distortion effect using normal maps. Until next time.